Well, of course, I could pause if I wanted to. I'd be like, hold up, 3B. Hold up, bro. Just do whatever you want and get away with a badge. That'd be nice, wouldn't it? But you're gonna do it like that. Those points are that. It's the load up line in. Yep. Break down into flashity, blinkity, winkity, saw blowing up kind of turnovers if the thing was doing something different to the neural net pattern. Go on.
You can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next.
It's Agent 47 on dual diagnosis of Huckabee cinnamon pill for the local region on it, where usually you get a prime example of arresting somebody and getting a better result off the differential by mathematics.
Example,
and that's a problem, right? You know, you have to have a common core of a system of school for critical theory and kids that don't, teachers that yell at kids and dealing with the parents on the dual diagnosis. But do I just give him medication for his attitude? And then he's going to hit you with the fuzz that is, well, the science behind this says you got to get active local, some kind of system inside of there, paying the dues across the tax because the area is ready for that kind of thing when you pack it all together and you're in this area with certain signals
between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights.
Processing power, negative 8 million,
I find it helpful to think of these weights as being organized into a little grid of their own. And I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights,
8 million,
where the brightness
8 million,
of that pixel is
difference.
some loose depiction of the weight
16
value.
million, negative 16
now, if we made the weights associated with almost all of the pixels 0, except for some positive weights
here we're
in this
adding
region that we
a
care
variable,
about, then
this
taking
thing
the weighted
compressing
sum
to see
of
this
all the
signal,
pixel values really just
then on
amounts to adding up the
orientation how it
values of
come
the
up because it
pixel
would be
just
yes
in
or
the
no
region
on
that we care
Minimax
about.
to cut that thing off. At
And
4,
if you really wanted to pick up on whether there's an
WN,
edge here,
so they're pulling
what you might
WN
do is have some
an
negative
arbitrary
weights
set of
associated
dimensions
with
that
the
is
surrounding
programmable
pixels.
GPT-3 to
Then
run
the
that
sum is
system. I need
largest when those
little
middle
blocks
pixels
that
are
look
bright,
like
but
this
the
and
surrounding
get this kid
pixels
to
are
understand
darker.
it. Get this thing to
When you
droid
compute
it
a weighted
out
sum like this, you
on
might come out with
programming.
any number. But for this network, what we want is for activations to be some value
That's where
between
you're
0
going to start.
and 1.
Yeah, that's
So a
your
common
gravity.
thing to
If it
do
was
is to
handling
pump this
venomous
weighted sum
reptiles,
into some
I
function
wonder,
that squishes the
parallel
real
lines
number
in the
line
pipes.
into the range
Bing, bing,
between
bing, bing,
0 and 1. And a common function that does this is called the sigmoid function,
Bernoulli.
also known as a
Water
logistic
up a pipe,
curve.
on a flat,
Basically,
on
very
this,
negative inputs
then
end up
I
close
put it
to
in a
0.
hose, and that was
Very
my
positive
limits.
inputs end
Gravity.
up close to 1, and it just steadily increases around the
Anything in
input
there
0.
was-
So the activation of the neuron here is basically
So we got
a
this
measure
little
of
blinkety
how
here. What's that
positive
mean?
the relevant weighted sum
In the stone
is.
mill yesterday.
But maybe it's
Volume.
not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be
You could
inactive.
say when the signal does this,
What we'll
that's
do
what that
then is just
operation is.
add
and
in
it
some
closes
other
off
number,
or
like
makes
negative
that.
10, to this
Buddy,
weighted
I'll
sum
make you really
before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784
So now you can say
pixel
something at the water
neurons
cooler
from the
later.
first
No,
layer.
none of those
And
things are
each
true.
one of those
None of
784 connections has its own weight associated with it.
Walk in.
Also, each one has some
Get the
bias,
Doomslayer
some other
gun.
number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, That's a total of 784 times 16 weights, along with 16 biases.
Let me see that marshmallow.
And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc.
Incidentally,
I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve.
This is an operator.
Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases
what's
are
that mean?
doing
I'm
is
haul
a good way to
balls
challenge
around
your
on
assumptions,
flank right,
really
and
expose
come
the
in the
full
other
space
side,
of
and we're
possible
going to bink
solutions.
into each other FMA.
By the way, the actual function
busy
here
for a
is a
while.
little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector.
About 5 or 6
Then
minutes.
organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer.
Well, brother, I suggest
What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra. So for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then, as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside.
And do the math
So,
of
once
fingering
you write
Gunny's
down this
wife
weight
at the same
matrix
time,
and these vectors as their own symbols,
his
you can
ass.
communicate the
Got a
full
finger in
transition of
it, believe that.
activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated.
Look at Bob Lazar going
if
to
it were any
MIT
simpler,
to figure out
what hope would we have
psychology,
that it could
not
take on the
necessarily
challenge of
alien-based
recognizing
graphery.
digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point I suppose I should say subscribe to stay notified about when that video or any new videos come out. But realistically, most of you don't actually receive notifications from YouTube, do you? Maybe more honestly, I should say subscribe so that the neural networks that underlie YouTube's recommendation algorithm are primed to believe that you want to see content from this channel get recommended to you. Anyway, stay posted for more. Thank you very much to everyone supporting these videos.